Now, let's make things a little more spicy, right? So continuous uniform distribution was simple, but I mean, it was telling us the story of the inverse transform technique. So this means the inverse CDF of continuous distributions or continuous random variables will always help us to generate random variates from that specified distribution. Now let's just practice this general idea for some more complex examples. Now, this time we have a continuous random variable x, which is set to follow exponential distribution with rate parameter lambda. Now let us remind ourselves with the probability density function of the exponential random variable, which is lambda times e to the power minus lambda x for all non-negative values, and it is zero otherwise, which means an exponential random variable cannot take any negative value. It can possibly take positive values, and the relative likeliness of the possible positive values are indicated by this exponentially decaying function, which converges to zero in the infinity, or random variable is much more likely to take values which are closer to zero, and it is less likely to take values which are closer to infinity, according to this relative likeliness function. The area under this function is equal to 1, obviously, and the cumulative distribution function is the integral of the PDF, which is 1 minus e to the power minus lambda x. And the CDF, as you can see, it is an increasing function over the domain of our random variable. In the non-negative region, it is an increasing function. Therefore, it is 1-to-1 and invertible. So 1 minus e to the power minus lambda x, the CDF, is invertible here. Now, what are the typical variables in real life which may follow exponential distribution? The most typical example is the inter-arrival times. Now, to a supermarket, to a bank, to any other service queue, the inter-arrival times of consecutive customers can practically be exponentially distributed. However, we are going to explain the details on that in the next chapter. So at this point, we should say that while the lambda, the rate parameter, is the expected number of arrivals per time unit, imagine this time unit is hour or minutes, okay? So this is the rate parameter. The inter-arrival times of consecutive customers can be exponentially distributed. So this can be one of the typical models for the inter-arrivals of entities into a queue. So customers to a bank, customers to a supermarket. So working lifetime of devices and components until the first failure can also be exponentially distributed. For example, imagine you have a computer and you are going to use it until it breaks down, and the time until the first breakdown or the first failure can be exponentially distributed. Again, it's going to be a time measure. So mostly the time between consecutive arrivals or the consecutive events or the time until the first failure can be exponentially distributed. In the second example, the rate parameter lambda is going to be the average number of failures per time unit. For example, if the expected lifetime of a computer is to work for 5 years and it is exponentially distributed, so this is the expected lifetime, the average number of failures per year is going to be 1/5. So the rate parameter is going to be 1/5. Please understand this distinction between the rate parameter and the average of exponential random variable. The expected value of an exponential random variable or its average is 1/lambda, and the rate parameter is indicating the inverse of the expectation. But the main thing that we are studying here is how we are going to determine the inverse CDF. Now the CDF is 1 minus e to the power minus lambda x. So what we are going to do is, again, we are going to use the inverse transform theorem, and we will say that the CDF of the random variable itself, x, is going to be equal to r. So 1 minus e to the power minus lambda capital X is going to be equal to capital R. And what we are going to do is we are going to take everything on the right-hand side and keeping x by itself on the left-hand side. So let's do this. First, let's take 1 to the other side. So it will become r minus 1. And if we multiply both sides with minus 1, then you will realize that e to the power minus lambda x will be equal to 1 minus r. Now, The next thing is to take the natural logarithm of both sides. So we take the ln function in both sides. So ln and the exponential function here will cancel out. Therefore, the power minus lambda x will be equal to ln of 1 minus r. And the only thing that is left is to take this minus lambda to the denominator of the right-hand side. So minus 1 over lambda, the natural logarithm of 1 minus r, is the random variate generator for the exponential random variable. So you see, we can use the inverse CDF for the exponential random variable as well to generate exponential random variates. But here's the problem. For the uniform random variable, the inverse CDF was very simple to calculate. It was just a subtraction, a multiplication, and summation. Now, for exponential random variable, it requires a natural logarithm calculation. Now, for computers, calculating the natural logarithm, it takes a lot longer than calculation of a multiplication. And calculation of a multiplication takes a lot longer than the calculation of a subtraction or summation. Summation and subtraction, these are simple operations for computers to do. Multiplication is a little harder. Division and multiplication, they are a little harder. And natural logarithm or square root or exponentiation, these are even a lot harder because, I mean, in exponentiation, you are doing a continuum of multiplications. And the natural logarithm is similar as well. Okay, these are complex operations for the computers to do. Actually, you wouldn't understand the difference. I mean, if you use a programming language or a calculator to calculate such values, you cannot understand the difference between the timing of these calculations because for your observation, they are still too short. But I mean, if you calculate 1 million multiplications and 1 million natural logarithms, you will realize the difference. So natural logarithm is a complex operation for our computers. Now, the long story short, we can use minus 1 over lambda, the natural logarithm of 1 minus ri, to convert a sequence of pseudo-random numbers into a sequence of random variates that follow exponential distribution with rate parameter lambda, or in other words, with average 1 over lambda. Okay, so you see this 1 over lambda here is the average value, and the ln of 1 minus ri is of course going to be a negative value because the natural logarithm of anything that is less than 1 is negative, right? So 1 minus ri is going to be somewhere between 0 and 1, and the natural logarithm of a value between 0 and 1 interval is going to be negative, and that extra negative sign here will cancel this negative value out, and that value is going to convert the average 1 over lambda value by scaling it to an exponential random variate. So this is the second practical example where we are going to generate exponential random variables using the inverse transform technique. It says, on a weekday between 8 and 8:30, the passengers arrived to Söğütli Çeşme metrobus station with a rate of 2 passengers per second. So Söğütli Çeşme metrobus station, it's a crowded place, right? I mean, we can say that according to the SPAS statistics, the average rate of arrivals is 2 passengers per second. At every second between 8 and 8:30, 2 passengers are arriving to that station. And we assume that the inter-arrival times are exponentially distributed. So the time between the arrivals are exponentially distributed. Now the rate parameter is 2 passengers per second. I mean, you need to check the unit of the rate parameter, 2 passengers per second. So this is a frequency measure, but the time between the arrivals, which is called the inter-arrival times, it's a time measure, right? So we are measuring the time there. Okay, so it says use the following random number sequence to generate inter-arrival times for 2 consecutive arrivals. We are going to use the first random number, 0.8825, and plug it into the inverse CDF of the exponential random variable. And lambda is going to be equal to 2, and R1 is 0.8825. The first inter-arrival time is 1.0707, which means from the start of the simulation, the first passenger arrives in the second 1.0707, and the time until the next arrival will be determined by the second random number, 0.3954. And again, we are going to plug this random number into the inverse CDF of exponential random variable, and rate parameter being equal to 2 will result 0.2516, which indicates that after the first arrival, the second arrival will occur, or the second passenger will arrive just 0.2516 seconds after the first passenger. So this is how we can use the inverse transform technique to generate a sequence of exponentially distributed inter-arrival times. I mean, we can use as many random numbers as we want, and we can generate as many random variates as we can. Basically, that is the rule. The methodology is the common ground here. It is the important part of the story.